Now's your time. So, welcome, ladies and gentlemen. We have uh, July 1st. So, welcome to July. We're going to talk about chapter 8 today, but we have some questions on chapter 7 real quick. So, let's just go ahead and get into that. Oh, you're not going to let me move this. Okay. All right. So, that will come in handy today because we're going to do dot structures some more. So anyway, Savannah asked, can I go over how to find the chemical formula of ionic compounds again? And I can't. So basically, when it comes to forming an ionic compound, say for instance, it asks you to put aluminum and chlorine together. Well, we're going to look up the ions of aluminum and chlorine. And see what charges they have, or we can look at the periodic table and look at their group number. Group 3, which is aluminum, is usually a positive 3. Group 7, which is chlorine, is usually a negative 1. But I have for you guys as well, if you want to have a quick and easy place to reference this, I've uploaded for you your ion chart. So you can click on that and it shows you a lot of common ions. So you can see that there we have common ions. And this is a PDF, so you should all be able to open it. So if we look for aluminum, you'll see that aluminum is over there in what's called trivalent electropositive, which just means +3. It's very old terms, you know. They like to make these. This one's very old, but it was the one that had a lot of ions on it. Sometimes they just kind of leave things off. So anyway, aluminum is a +3 ion. If you want, you can just label these things +1, +2, +3 instead of monovalent electropositive, because those are way fancier than what we need. But it also shows you a lot of the different D and F block elements and how they have multiple charges. So that was one of the reasons why I liked this one in particular. So anyway, this is a chart that you can use to help you look up ions if you don't have it down on the periodic table. So anyway, we can see that aluminum's over there in the +3 group, and chlorine is down there in the -1 group. So we have aluminum up here. We have aluminum right here, and we have chlorine down there. So this is a 3+ ion, and this is a -1 ion. This plus this, the overall charge of our aluminum and chlorine has to be 0. So we need enough aluminums and enough chlorines when we mix them together to get to 0. And the easiest way to do that is just to take the charge here and put it down there. So that's why it's called the crisscross method. And take the charge here and put it down there. So that means we should have 3 chlorines. Because +3 plus 3 times -1 is equal to 0. Another way for you to do it, if you want, is you can draw yourself a picture. And aluminum is a +3 box, so plus, plus, plus. And chlorine is a -1 box, so -1. So 1 aluminum will not be balanced by 1 chlorine, so we're going to need 3 chlorines to give us AlCl3. And then tomorrow, we'll learn that this thing is called aluminum chloride. So that's how we make ionic compounds. We want to balance their charges. Now, say for instance, we had, when can we not just simply use the crisscross method? And the answer is when the numbers are whole numbers. So for instance, say we had, when they're factors of each other. So say for instance, we had some lead 4 and it was going to be hanging out with some sulfur, which is -2. If we do our crisscross method, you might want to say that this is Pb2S4. But when it comes to ionic compounds, they don't want to do this. They want to have the absolute simplest ratio. So this isn't true. So you want to simplify this to just lead S2. So both of them add up to 0. It's just you don't want in ionic compounds, because today we're talking, or yesterday we talked about ionic. Today we're going to talk about covalent. In ionic compounds, you want the simplest ratio. Now, sometimes this doesn't happen because you can also have what's called polyatomic ions, which you can see in here. You'll notice that some of these ions, like say for instance, ammonium here, and then we have acetate and sulfate and nitrate, all these things. You'll notice that there's more than one atom inside of the ion. And so sometimes you'll get something that looks like it should be simplified, but we just treat that polyatomic ion as one ion. So a great example of this is hydrogen. Hydrogen is usually +1. And then if we add oxygen, that's usually -2. And of course, this gives us water. Water is not an ionic compound, but for the demonstration purposes, we're going to use that. Well, there is a polyatomic ion called peroxide, which is actually O2 and has a -2 charge as well, and at which point you get hydrogen peroxide, which looks like this. And you're thinking, well, I should simplify that because it should have the simplest ratio. And the answer is, don't do that. Just simply leave it the way it is. We treat polyatomic ions like they're one thing. So in this case, if we were to draw our picture, this is 2 hydrogens hanging out with an oxygen. Well, in this picture, this is 2 hydrogens hanging out with a peroxide. So you'll notice that even though there's 2 O's in there, we're just kind of treating it like AO2. So another good example of this would be like sulfate. So say, for instance, we have aluminum and we're going to mix it together with some sulfate, -2 for the sulfate. We're still going to do the crisscross method, but now we get Al2, but instead of taking that 3 and putting it throughout, what we're going to do is we're going to use parentheses. So this is going to be SO4 and we do 3. And the reason for this is that this grouping of ions here called the polyatomic ion is going to stay together. So if we were to draw a picture of this, what this would look like, we'd have 2 aluminums and then the sulfates, the 3 of them would be all around it, and they would be together as a sulfate. They wouldn't be split up into individual atoms. They would be stuck together as SO4. Today you'll learn that SO4 looks like this. So yeah, that's how that works. So those are polyatomic ions. So if you have more than one polyatomic ion, you want to use parentheses around it. You just don't want to change the numbers on it. We'll talk more about polyatomic ions in the next chapter when we talk about naming and all that kind of stuff. The way I'm following the book to make it easier on you guys, but the way that they have these chapters set up is just it's a little all over the place. I usually like to start with what type of bonds there are, and I go through all 3 types. Then I talk about naming them, and then we get more into covalent stuff, but you know, it is what it is. So speaking of jumping right into covalent, are there any more questions on ionic stuff? So if you're thinking about the test, you know, things I'll ask you on the test, you know, pretty simple stuff would just be like, what would the formula be if you combined, you know, calcium and sulfur? And so you would look, it would probably tell you the charges because, you know, just for sake of time. And it'd be like, what is the formula that can happen here? And of course, you know, it should just be CAS, but there might be Ca2S2, you know, because, you know, that's the kind of the thing it's asking you, which one's the correct one? And the answer is that one's correct because it's the simplest ratio. We want to make them zero. You can think of it like this. If you, they're like hungry, right? This guy's twice as hungry. This guy's -2 is hungry. And so they're going to get together and they're going to eat until they're no longer hungry. So they're going to bond to where their charges equal 0, because remember, their attraction force is their positive charge or their negative charge. So if they get together with something else that is the opposite charge of them, then they don't have a force anymore. And so they are, they're formed. In reality, that's not actually what happens. Magnets, as you guys know, they don't just stick to one other magnet. So for instance, if we looked at sodium chloride, that makes NaCl. But if we were to actually look at sodium and chloride up close, the sodiums would be these little red circles. And the green circles would be chlorines. And then this shape would look like a square. So it would make a big square shape of this. And that's why salt crystals are squares. So pretty cool. All right, so if there's no other questions on ionic, we can move on to covalent. There's another, some iron, the ferrite, fool's gold makes a really cool square structure too. So, but that's, you know, the crystal and lattice structures are not high school level, so you don't have to worry about that. Okay, so let's talk about covalent today. So yesterday when we talked about ionic, what was happening, say we were looking at our sodium atom, is we had one extra valence electron, and underneath we had our full 8 valence electrons. So in the case of sodium and chlorine, they would exchange electrons. And same thing, chlorine has 8 underneath it. So this guy has a big hole, this guy has an extra one. They exchange electrons and we get sodium positive, chlorine negative, and they're just attracted to each other because of their opposite charge. That's an ionic bond right here, the electrostatic attraction between their opposite charges. So what's going on with covalent? Well, electronegativity is the answer. So if you remember from last unit, we talked about electronegativity, and that was the strength of atoms to pull on each other in a bond when they try and steal each other's electrons. So if we look at that's the one I gave you. Let me show you another chart. Desktop flash drive. Bonding. Oh, come on, silly man. There we go. So if we look at this picture of the periodic table in terms of electronegativity, right here, we can see that we have the highest electronegative elements are the negative ions or the nonmetals, and the lowest electronegative elements are the very reactive metals in the lower alkali and alkaline earth metals. And then they're kind of rainbow in between. So basically, electronegativity is the desire for the electrons. So what happens when you have a covalent system is, say for instance, you're that chlorine, and that chlorine wants some electrons. It wants to fill its valence shell, but there's no sodium around. And you have your electrons here. You have, 2 in your lowest shell, and then you have 8 in your second shell. And then in your final shell, you have 7. So 1, 2, 3, 4, 5, 6, 7. But you got a hole right here in your valence shell. You'd like to have 8 there, but you don't have anything to take an electron from. You're in an environment where the only other substance is just another chlorine. So what can you do? What you can do is you can share. And you can do what's called orbital overlap. So now this chlorine's empty box will fit the other chlorine's electron, and this chlorine's empty box will fit that electron. And so they overlap. So that now it looks like, if we just look at their outside energy levels, it looks like they both have 8 valence electrons, but they did not exchange them, they shared them. And this bond right here is called a covalent bond, where we have the 2 outer orbitals overlapping and each exchanging, or basically each giving an electron to the other to fill their valence shell. Now, it's real ugly when you try and do it with the orbital diagrams, but it's really easy to do with the dot diagram. So for instance, if we have chlorine and we have another chlorine coming in, this guy has 7 valence electrons, and this guy has 7 valence electrons. And you'll notice that they both want 8. So what they can do is they can come together and they can overlap their orbitals, and it will look like they have the noble gas configuration of, in case of chlorine, they want argon. So this guy right here can move over. And now you see what we have here is a sharing of our 2 electrons right here. This electron sharing, or valence electron sharing, is what we call orbital overlap, or hybridization is another way to put it. And so covalent occurs when atoms have strong electronegativity, so they're unable to take each other's electrons, so they must end up sharing. This right here is what's called a single covalent bond, or a single bond. And the reason why it's called a single bond is because they've only overlapped one orbital. Their other orbitals out here are already full, and so those guys are what we call lone pairs. Any electron that is by itself is called a bonding electron. So chlorine had one bonding electron each, so they bonded one time. So we get what's called a single bond. When we get rid of all this mess that I drew over here, we have what's called a Lewis dot structure. So the two chlorines coming together with the dots around them like so is called a Lewis dot structure. We can then make this even simpler by drawing what's called a structural formula. So this is a Lewis dot structure, or a dot diagram. And we can then simplify this by writing it as what's called a structural formula, where we ignore the lone pairs, we don't need them. You can write them if you want, but you don't have to. And then everywhere there's a bond, we just draw a line. There's only one bond, so we only draw one line. And this is called a structural formula. So usually we want to start off with drawing our dot structures, and then we get used to kind of figuring out how many bonds things want, and then we can kind of just draw the dot structures or the structural formulas. So sometimes in a structural formula you'll see it with the dots, and again, this isn't needed if you don't want it. You can draw it if you want. It's up to you. So those are what are called single bonds. And obviously, if there's a single bond, then you can draw a double bond. So what's an example of a double bond? So let's look at sulfur. Sulfur has 6 electrons in its valence shell. And so if the only thing around is another sulfur, oops, let's do black. Then they have no choice but to bond together. So what we have here is we have our first bond, but you'll notice that these guys right here are also bonding electrons. They're also available to bond. So what we will get is a double bond. And so if you go and like Google, Lewis dot diagram for sulfur, there's a couple ways you might see it. You might see it like this, where you just have the dots like that. Or you might see it like this. Both are right. I tend to like the top one simply because it just kind of stays consistent with the organization. So these would be our two possible Lewis dot structures. So what does the structural formula look like? The structural formula will just be the S's, but now we draw 2 lines because we have 2 bonds between that one atom. The oxygen that we breathe is O2. If it wasn't O2, then it wouldn't work for our respiratory system. The fact that it's oxygen with a double bond to another oxygen makes it a great way of moving electrons around. And that's why our metabolism, part of it is what's called the electron transport system. And the ultimate place for those electrons to go is onto the oxygen at the end. So that's a double bond. And so if there's single, if there's double, then you're probably wondering, hey, is there triple? And the answer is yeah, there's triple. And the things that can do triple bonds are things like the carbon group and the nitrogen group. So let's go ahead and do nitrogen. Nitrogen has 5 valence electrons. So 1, 2, 3, 4, 5. And if the only other thing around is another nitrogen, then we will get these two nitrogens wanting to come together and bond. And so you'll notice that we have a couple of our bonding electrons coming together to form a bond. But now we have bonding electrons up here that can bond and bonding electrons down here that can bond. And so we have a triple bond. So the Lewis dot structure for this will be N, N, and there's 2 ways to do it. You can do it just like we had it before, or you can do it like the other way I showed you, which is putting the electrons together like that. Both of those you might find on the internet. And the structural formula for this will be 3 lines, because they bond 3 times. 78 to 80% of the atmosphere is N2, nitrogen gas. And it's extremely inert because, as you can imagine, the strength of the covalent bond is going to increase the more you're bonding. So single bonds have a lot of strength, but double bonds are stronger and triple bonds are even stronger. So this is a triple bond. So if there's single, if there's double, if there's triple, then is there quadruple? And the answer is no. Carbon, the carbon group, is our only group on the periodic table that has 4 bonding electrons. So if carbon was going to hang out with another carbon, then they're going to come together and they're going to bond like so. And you'll notice we get 1 bond, so single, then we get double, then we get triple. But you'll notice that these bonding electrons out here are not in proximity of each other. They aren't, those 2 electron orbitals aren't able to get near each other, so you can't overlap them. And unfortunately, we don't have any quadruple bond. So if you want to actually look at the orbitals and say, like, what is actually happening here? Well, if we look at our blue circles as our S, then one of our single bonds is going to be the overlap of our S orbital. And then we'll use green for our P orbitals. And the PY orbitals are in proximity to each other, and so they can overlap. And our PZ orbitals are in proximity of each other, so they can overlap. But unfortunately, the px orbitals are out there. And so that electron that's hanging out in here, there's no way for it to overlap. And so we can only get a triple bond. So we have a bond here, we have a bond here, and we have a bond here, but we don't have the orbital, we don't have the ability to overlap that p orbital, and so we cannot get the fourth bond. Which is good, because we would not exist if carbon could just quadruple bond itself. Carbon is the secret to all things. Life, because of its ability to form so many bonds, it can form so literally infinite numbers of compounds, and that diversity is what's needed for life. So pretty cool. So we can now start building molecules, all kinds. Say, for instance, we want to put together some hydrogen and water. So we have some hydrogen, and we're going to put that with some oxygen. So we're going to draw our Lewis dot diagram for hydrogen, and we're going to draw our oxygen Lewis dot diagram. And so now we're going to put these guys together. So this guy right here is going to come over, and he's going to go right there. Boop. And we want to, well, let's draw another one. And then we have another guy over here who's going to come in, and we're going to get that bond right there. So this will give us the structural formula of H-O-H and give us the formula H2O. Water is a covalent compound. The electronegativity difference between hydrogen and oxygen is not big enough to create ionic interaction. The hydrogen does not lose its electron to the oxygen. They are sharing them. Now, this sharing is not equal. It is what we call unequal sharing, otherwise known as polar, and we'll talk more about that in a second. So one of the big issues we have here on the planet is that we're making it really hot, and the chemical that is responsible for that is what's called a greenhouse gas. And the reason why this is a problem is because this molecule, which is carbon and oxygen, when it comes together, it forms an extremely stable molecule that is really good at insulating heat energy. So the light comes in, hits the ground, bounces back up, but instead of being able to float back off into space, it bounces off the CO2 here and stays on the planet. This is great if you don't want to freeze to death every night, but not so great if you don't want to bake the next day. So if we look at our dot structure here, carbon has 4 available bonding electrons, and oxygen has 6. Total valence, but only 2 bonding electrons. So when we put these guys together, like so, you'll notice that we have lots of bonding electrons that we need to do something with. So what we're going to do is we're just going to move this electron down here. And now we can have a double bond. 1, 2. But what about these guys over here? Well, for that, another oxygen is going to come in and bond with the carbon to give us the Lewis dot structure of CO2. Like that. Another way you could write it is, of course, you can go like this. If you look it up online, where they will have the carbon doing this. Both of those are fine. This one down here is the one I usually tend to go with. And the structural formula for this then will kind of look like a motorcycle. And this is CO2. It is an extremely stable molecule. Carbon and oxygen love to come together and form CO2 and be happy with like that for a very, very long time. Billions of years if they can get away with it. Millions if there's some sort of carbon cycle. And so that's the issue. If this was a volatile molecule like carbon monoxide, then it would destroy itself as soon as it came in contact with something because it would react and become something else. When it comes to CO2, this requires natural systems like microorganisms or other types of life, for instance, like marine life, which will absorb the CO2 as CO3, which is in the ocean, and turn it into their shells. And then, of course, plants, what a plant is made out of is actually carbon dioxide. They breathe in the carbon dioxide, react it with water and other substances like oxygen and whatnot, and they turn it into the sugars and the wood and all the other stuff that it makes up a plant. So that's one of the things that is an issue with this guy here. And this particular molecule contains double bonds. So what if you got a big mess? So what do? Say, for instance, the problem asks you to say, well, what is the formula of C2H6? Like, what is the structural formula of that? Or what is the Lewis dot structure of that? And so the answer is, how do you set this up? Where do you start? And so the where you should start is with the atoms that have the most bonding electrons. So what I like to do is I like to draw the dot structures of everything that I'm going to need to put together. So I've got my 2 carbons and I've got a hydrogen, and I'm going to need to slap these all together so that every single one of those electrons is used up. So when it comes to the atom that has the most bonding electrons, this is probably going to be our center atom. And since we have 2 of these carbons, they're probably going to both be center atoms. So we're going to want to bond them together. You lassoed them. What happened there? All right. So we're going to need to bond them together at least one time. So now we have our bond with the 2 carbons, and we notice that we have 6 bonding electrons left over. And it just so happens that we have 6 hydrogens that need to go around this thing, and each one of them has 1 bonding electron. So chances are what this wants is for us to just do exactly that and put them all around. And this will give us the structural formula for CH6. Now, notice that this says C2H6, and you're saying, well, hey, that's not the simplest ratio. Well, covalent is not about sharing, or sorry, it's not about coming together to make yourself 0. They're coming together to share all of their electrons. So a not simplified ratio is 100% in the works. That is how you might have to share every single one of your electrons until you are completely happy with your full valence. Okay. So now when it comes to sharing, you can have what's called equal sharing and unequal sharing, otherwise known as polar and non-polar. So polar covalent bonds are what happens when the electronegativity difference when the electronegativity difference is larger than 1.6 or 1.7, I think your book says 1.5. We'll just say 1.6. So when the difference is about 1.6, you have what's called a polar covalent bond. Anything larger than 1.6, so 1.7 plus, this is just going to be ionic. This strength difference between them means that the higher electronegative element is going to be able to just strip the electrons straight off of there. When it comes to polarity, I just want you to know the definitions of those things. I'm not going to have you guys tell me which atoms are polar, which are nonpolar. I just want you to understand what's going on here with polarity, because it will be important for other chapters in this year. So as you can see, water is a very, very polar molecule, and that's because we have hydrogen here with its kind of middle of the road electronegativity, and we have oxygen here being the second highest electronegative element. But when we look at their numbers, oxygen is a 3.5 and hydrogen is a 2.1. And so that is not enough to make them ionic. Pretty close, but not enough. 1.4, highly polar, but not ionic. If we take hydrogen and fluorine, for instance, fluorine is a 4.0 and hydrogen is a 2.1, well, that's a difference of 1.9. And so in the case of hydrogen reacting with fluorine, we will get the exchange of electrons and we will get the electrostatic attraction. And so water, H2O, is a polar covalent bond, but HF is a ionic bond. Carbon and hydrogen is very what we call slightly polar. We have 2.8 and we have 2.1. So that's a difference of 0.7. Because when it comes to nonpolar, that's an electronegativity difference of anything less than 0.3. So if you have an electronegativity difference of less than 0.3, you are considered nonpolar. So when atoms bond together with themselves, say for instance the oxygen that we breathe, that's going to be what's called a nonpolar bond, because both of these things are both 3.5, so the difference between them is 0. So they are nonpolar. So what is polarity? Basically, you can think of it like little magnets. So things that have polar bonds in them can act like little magnets, and things that don't have polar bonds in them will just act like oil, where they will not have a significant attraction to other things. So that's how we draw structural formulas, how we make covalent compounds. But let's talk about their shapes in 3 dimensions. And this is a theory called valence shell electron pair repulsion, otherwise known as Vesper theory, even though it doesn't really spell Vesper. But this stands for valence shell electron pair, also pair repulsion. So what does it mean? Well, let's take a look at a compound by the name of methane, CH4. If we do the dot structure for methane, we have 4 dots here on the carbon, and the hydrogen comes in with its 1 dot and shares 4 times. So this gives us CHHH. Well, in a 2-dimensional world, this is great. They just draw them 90 degrees away from each other. However, is that what actually happens in reality? Because in reality, this is a ball, a sphere, and this is 4 other spheres on it. Well, they have, instead of just having a box being able to try and make themselves the absolute farthest away they can from each other, they have an entire sphere they can move around on. And so what will happen? Well, it turns out the carbon, if we look at methane, actually kind of looks like this, where this one is kind of coming at you, and this guy is kind of going away from you, and these guys are kind of pointing up in space. It kind of looks like a tripod. That's Vesper theory. Vesper theory basically says that the valence shell electron pairs, or basically the bonds or the lone pairs of the electrons, will push on each other because they're all made of negative electrons. And so their goal will be to get absolutely as far away as they possibly can from each other. So when it comes to Vesper theory, what are the different shapes? Well, first off, we're going to classify them into the number of atoms that are in the bond. So the first one we're going to talk about are 2 atoms. So if you have 2 atoms in your molecule, there's only one shape you can make, linear. You don't have a center atom, you only have 2 atoms, and so the best possible way for them to get away from each other is for them to have a bond angle of 180 degrees. What's a bond angle? Well, what is any angle? If we look at a circle and we go like this, then we have an angle. Well, I drew a 90-degree angle here, and what we have is 1 point there, 1 point there, and 1 point there. But if we only have 2 points, that angle has to be 180 degrees. It can't be anything else. So we're going to need 3 or 4 or 5 points in here to be able to talk about the different angles that are formed by the molecules. So all 2 atom shapes are linear. So the hydrogen in the air, the hydrogen that we form to run on fuel cells is a linear molecule. The oxygen that we breathe is a linear molecule. The nitrogen that's in the air doing nothing is a linear molecule. Any 2 atom hydrochloric acid is a linear molecule. Any 2 atom shape is linear. So now from here on out, what we're going to be looking at is what's called the center atom. The center atom is going to be our most important part because that is going to be our fulcrum of our angle. And it's going to determine, where the other things are in relation to others. So we have 3 atom shapes, 3 atom molecules. So 3 atom molecules can either be linear or they can be what's called bent. As we know, linear molecules are 180 degrees, bent are 104.5 degrees. So what is the difference? Well, it's all about the center atom. And so no electrons left unbonded on center is what causes it to be linear, and then electron pairs left on center is what causes it to be bent. So what's the difference here? Well, let me show you. Say, for instance, we had carbon dioxide. Carbon dioxide has carbon bonding with 2 oxygens, where carbon is going to be our center atom. This gives us 2 options. Well, a bunch of different options, but basically we could draw it like this if we wanted to. But we could also draw it like this. So which one's right? And the answer is this one, right here. Why? Because there aren't any valence shell electron pairs on the central atom left to do any repulsion. So the best way for these electrons to get away from each other is to go on opposite sides of the center atom. But in the case of water, water is two hydrogens hanging out with an oxygen, and you'll notice what's left over. Valence shell electron pairs. They're left over on the center atom. So instead of writing H line O line H, that would suggest that it was linear. In fact, it looks like this, because those electron pairs are up here and they are bending the shape. They are pushing on the bond to make the shape be bent. So if you're looking at the shape of a molecule, you want to first say, how many atoms does it have? If it has 2, it's always linear. If it has 3, it could be linear or bent. So the next question you ask yourself is, how many electron pairs or electrons are left on the center atom? None, that's going to be linear. Some, that's going to be bent. Water is a bent molecule. And because it is bent, it has the amazing properties that it has. If water was not bent, if it was straight, it would not be a liquid. It would be a gas, and we wouldn't exist. We wouldn't be having this conversation. So we talked about 2-atom molecules. We talked about 3-atom molecules. Next is obviously 4-atom molecules. So let's talk about 4-atom molecules. And there's a really good 4-minute video on this if you want to review it later. So 4-atom molecules can either be what's called trigonal planar, or they can be trigonal pyramidal. So they either form a peace sign or they form a pyramid. The bond angle of trigonal planar is 120 degrees. The bond angle of trigonal pyramidal is 107.5. Some people just say 107. It depends on your particular text. In the case of the 4-atom molecule, we want to look at the center atom. And for planar, the center atom has nothing left in the center. For the trigonal planar, the center atom is going to have lone pairs. So what's a good example of this? Well, let's take a look at something like aluminum chloride. Even though aluminum chloride is technically an ionic compound, aluminum with its 3 electrons here, we could draw it like this, and chlorine with its 7 electrons could draw it like that. But what you'll notice is that there is nothing left in the center of the aluminum. On aluminum. Aluminum has 3 valence electrons. It uses every single one. So there's this big space over here that's just not being used. So what will happen is the atoms will spread themselves out so that they're absolutely as far away from each other as they can. And this will give us the 120-degree bond angle. So 4-atom molecules, center atom has nothing left. That will result in trigonal planar. So for trigonal pyramidal, let's say, for instance, we have ammonia. Nitrogen is our center atom here. And if we draw our dots and we put hydrogens on there, you'll notice now, instead of that big empty space like we had on the aluminum, we have a lone pair. So the lone pair is going to take up space, and so the hydrogens have to bend out of the way, and we get the pyramid. And the reason why it looks like a pyramid is it looks kind of like where this one's coming at you, and then that one over there is going away from you. So it looks kind of like a pyramid. So 4 atoms, nothing left, planar. Something left, pyramidal. And then finally, the last thing we're going to talk about today is 5 atom shapes. Now, what about 6 and 7 and 8 and all that? And the answer is they might have names, but usually what happens is that after 5 atoms, the shapes are really just kind of sticking to each other. And so their bond angles are still going to be the same as these 5 basic shapes. And so we stop trying to give them their own shape name, and we really just kind of start looking them as chains or larger molecules. But there are a couple more shapes on top of this, but we're not going to really need them for this level. So all 5 atom shapes are what are called tetrahedrals. There is no other shape besides tetrahedral for 5 atoms shapes. Tetra means 4, hedral means zone, so it means 4 zones. And basically, it's a tripod. It has a bond angle of 109.5 degrees. And usually the center atom has nothing left on it. And this has to usually be the carbon group. So we go back to our original example here. We have our methane. Methane is going to be CH4. And so we could get 90 degrees away from each other, but it's best if we do this kind of tripod system here where we have one sticking up. And this is called tetrahedral. Now, I have a cool program that will show you this kind of stuff. On my other, is it on my other computer? Yeah. I'm on my little laptop so I can write on it. I'll have to show it to you on the other thing. But either way, a good thing to see these things in 3 dimensions is to go over here to the module, and the video that talks about Vesper Theory is very short and shows you all of the shapes here and their angles and what they look like in 3 dimensions. So, oh, I put the wrong link in there. Let me fix that for you. I probably just doubled up on that. So yeah, that's going to be that. I'll fix that right now so you can watch that video. But that's it for today. I'm going to stop recording.